One of the big kinds of series that we're going to deal with called the geometric series, and this is one of the very few series that we can actually find an exact summation for. We can find an exact value for the sum of a geometric series. And all a geometric series is you have some ratio r, that I'm going to call it here, raised to the n power. And you can have a number in front, a, that's fine as well. But when you have that a times r to the n power as your summation, you can use this formula to be able to find your summation. Now that only works if you have an r value, a ratio that is a legit ratio between 0 and 1. If r is bigger than 1, either positive or negative 1, further away from 0 than that, then the series automatically will diverge instead of converging. So to show you what it looks like, let's just jump right into it. So get a couple of examples up here. So this first one should be very straightforward and easy to look at. The format we have is that we have a times r to the n power. Well, that's good. And r is between 0 and 1. So this is a converging series. And we can just use straight from this formula over here. 8 is the number in front. 1 minus 3/4 for the denominator. 1 minus your ratio. Just that simple. So it's 8 minus 1/4. So when you add all those numbers up, you're going to get 32 as your answer. And I mean, you could go and actually try to map it out just to see, but if you plug in 0, you would have just 8. If you plug in 1, you would have 6. If you plugged in 2, for example, now you have 9 over 16. Now you have, what would that become? 18 over 2. Did I do that right? Not sure I did that right. Let's try that again real quick. If you plug in 2, you have 9 times 8 and then divided by 16. So you should have an extra 4 on the bottom. So it should be 9 over 4. And you can see the numbers are getting smaller, as they should when you're doing this, excuse me, these sequences in series at exactly what we want to see happening. So we should be able to find an exact value, and look, there it is. Now, a lot of them, when we're doing these problems, are not going to look perfectly nice and look perfectly like this AR to the n format. But guess what? It is. This one I can rewrite very easily. 3 is just a number. It can kind of stay out front. 2 to the n power, but it's on the bottom. So 1/2 to the n power, the entire thing to the n power. Because 1 to the n, no matter what n is, it's always going to be 1. So that's just kind of your way that you can rewrite it, and now we can use the formula again. 3 is the number out in front, 1 minus 1/2 in the denominator, so 3 over 1/2, which becomes 6 for your summation of that geometric series. Okay, let's look at a couple more now. This one looks a little tricky because we're not going from n equals 0. That's important. That formula only works if you begin with n equals 0. Well, sometimes what you should be able to do is you should be able to rewrite something in a way that you can make it so n equals 0. So basically, if you plugged in 1 immediately, you would have 4 to the 0th power. Then your next value would be plugging in 2, which should be 4 to the 1st power. Well, how can I rewrite that in a way that if I start with n equals 0, well, it's still 1 on top, but now I'd have 4 to the just n power. I still have 4 to the 0th first, and then 4 to the 1st, and then 4 to the 2nd, all showing up. So I can say that this then is just the easy series of 1 over 4 all to the n power. So sometimes you just have to manipulate the way that your sequence is being written. So when you do that, we can use the formula now. There's no number in front, so we call it just 1. 1 minus 1/4 is your denominator. So you get 1 over 3/4, which becomes 4 over 3 for your answer. All right, one final one that we're going to look at. This is an example of one that does not rewrite very easily. We're not starting at n equals 0. I'd have to go back to get it to n equals 0, which means this would have to become like a minus 2. Well, let's do this. We're going to have to do this a couple of different ways. To be honest, I just thought of this second way. So the way I'm going to look at this, if I wanted this to be n equals 0 to infinity, kind of like we just said there, it'd be negative 1/2 to the n minus 2 power. Well, let's see if I can rewrite that even more at this point. So n equals 0. I still have the 4 out in front. I can have negative 1/2 to the n, but I also have this minus 2 power. So that means the way that your exponents work is that you have something that looks like this. Excuse me, that you just add your exponents together when you have a power to a power. So if I can keep simplifying that, I'm going to get it closer and closer into this geometric series format. So this negative 1/2 to the negative 2nd power is going to become, it would become negative 2 to the positive 2 power. So that would become just 4. So this value right here is 4. So I have now 16 times negative 1/2 to the n, which now I can use the formula 16 over 1 minus negative 1/2. So 16 over 3/2, which should mean 32 over 3 is my answer. Now, let me go back here because I definitely made a big error. If we move this to n equals 0 to begin with, we should have said, well, let's take a look. Our original value was as an exponent of 0. So if I move my original down to 0, that means this has to be n plus 2 to maintain that my first exponent is, excuse me, still a 0. So this should be n plus 2 this entire time. So when we do that, not much changes, except that when we evaluate this, negative 1/2 times negative 1/2 is 1/4. This becomes just a 1 out in front. So it should be 1 over 3/2. So this answer should have been not 32/3, but 2/3. That makes a lot more sense. So apologize for that, but now let me show you another way that you could have looked at all that. Just happened. So let me show you one other way that we can look at analyzing this problem from the very beginning. We could say that this summation is just exactly what it is, or we could say, well, what if we had started at 0 instead of 2? It's still the same formula, but we're taking away, if we had plugged in n equals 0, and taking away if n equaled 1. Because we're starting at 2, we'd have to take away this summation here that we just rewrote, but instead we're taking away when n equals 0 and when n equals 1. That allows us to start at 2. So if we did that, well, this part right here now is that geometric series. So that's beautiful. We can just use the formula of 4 over 1 minus the ratio. When we plugged in 0 for the, so this is the term n equals 0, this is the term when n equals 1. When we plug those values in, this guy, 4 to the 0th is, or I'm sorry, ending the 0th is 1, so that's just 4. And this minus here becomes minus a negative 2, so that becomes plus 2. So when we simplify that, we have 4 over 3/2 minus 4 plus 2. Well, that gives us 8 over 3, and then subtract 2 from that. When we subtract 2 from that, that gives us 2/3, which is the exact same answer. So 2 different ways that you can evaluate a problem like that. Those would be the absolute most complicated they would ever ask you to find a legit full numerical summation to it. But there's geometric sequences and how we can use them and find values.